Good morning, and I'd like that video for my website also. Before I get into the presentation proper, some perspective. There was a report came out last year from the International Energy Administration about energy efficiency. It said if you look at all the energy efficiency investment from the mid-70s through 2010, it accounted for approximately a 35% reduction in energy use in the year 2010. So a couple of things come out of that. You can think big numbers when you think energy efficiency. The second thing I want you to think about, most of that energy efficiency came from what we call component efficiency. You put a new light bulb in, you have a more efficient engine, a better window. I'm going to talk about what I would call multidisciplinary and system approaches to efficiency. So I'll cut to the chase, the question everybody asks. How do you turn drywall and concrete into storage? It's going to be a really hot day tomorrow. At 1, 2, 3 in the morning, I turn the chiller on. I make it uncomfortably cold. You're not in the building, so you don't care. All that cold bleeds into the concrete and drywall. During the day, it bleeds out, and it takes a big divot out of the air conditioning load. I can control the depth of charge and the timing by a temperature control strategy I send to the building. It's that simple. Now, when I say uncomfortably cold, we once accidentally got a building down to 69 degrees, so think 70 degrees early in the morning before you get into the building. But when you get into the building, I'm up in your comfort range. So not that cold. The 20 to 40%, a couple of stories there. We love LEED Platinum buildings. They're well documented, well operated, bright engineers running these buildings. We're plug and play in a LEED Platinum building. We're storage. Storage is a good complement to just about anything that's in a building. So the better their equipment, the more advantage they can take of storage, the more advantage we can take of their features. The other 20 to 40% story. There was a California study, and California does great studies. They looked at thermal energy storage, and they said, let's assume that the thermal energy storage is 100% efficient. It's just going to shift energy use from day to night. At one end of the state, they determined that just shifting energy from day to night would reduce source emissions and energy use by 20%. At the other end of the state, it would reduce source efficiency and energy use, emissions and energy use by 40%. How does that happen? You're unloading inefficient plants at the margin during the day. You're loading up more efficient plants at the margin at night. So source efficiency is important to us. My background is grid operations and markets. We always think in terms of source efficiency, not in terms of site efficiency. Large buildings in large cities, because that's my background. I've managed transmission planning, transmission services in large cities for years. That's where we have high and volatile prices. That's where we spend billions of dollars on underground transmission and distribution. So that's where the largest dollar opportunity is for storage. We're diurnal. There's a lot of people that optimize in real time. We get to play a whole 24 hours. Financial risk management is my favorite application. Think in a hotter than normal summer, you're going to have higher than expected electric prices. So we put a lot of dollars on the table on a really hot summer. In a mild summer, we don't perform as well. There's not as many opportunities, but you don't really care because your electric bill is pretty low anyhow. What gets us up in the morning? We know that if you can control even a portfolio of 50 buildings in a large grid congested city, we can start to affect price in that city for everybody in the city. In our markets, rule of thumb, if you can control 7 to 10% of the load in a market, remember these cities are geographically small markets, you can control 7 to 10% of the load, you can take prices out at the knees. If I'm using drywall and concrete, obviously no capital expense. I don't need any space. There's no equipment. Infinite cycles with no degradation in performance. The drywall and concrete doesn't wear out. I say dramatically outperforms batteries. I'll take you to the next slide. This is a graph of 4 months of operations at the Willis Tower in Chicago. We don't do a whole lot of 4 million square foot buildings, but they approached us, and we have some really good numbers and stories to tell about Willis Tower. We charged the building up at night to the tune of an extra 630 megawatt hours. That had the effect of displacing 1,530 megawatt hours during the day. Now, you think storage and you think you can't be more than 100% efficient, and we're not. But at night, I'm charging, you know that running your air conditioner at night is more efficient than running it in the middle of a hot summer afternoon. And in these buildings, I have multiple chillers, so I get to pick the most efficient chiller to operate at night. And then I get to control what point on the chiller efficiency curve I get to run that chiller. So I have a lot of choices at night. I play a lot of those same games during the day. I can play arbitrage chiller efficiency curves. I can play good chillers against bad chillers. But that's at 2.5 times. You should also know at Willis Tower, we only controlled the temperatures in 13 of 100 floors. Now, they were closer to the base. It was roughly 20% of the floor space of the building. But controlling 20% of the floor space of the building, I get that kind of performance on the entire building air conditioning system. So controlling chiller loading at the margin is the goal. I don't need that much storage. We're in the cloud. We get price feeds. We get weather feeds. We get some status information from the building. We send control strategies to the building. This is all automated. Demand response up in the upper right-hand corner. I come from that industry. We controlled this building on 78 weekdays over 4 months. On 62 of those days, we deployed it in the PJM Economic Demand Response Program, making money from the grid. If you're not a LEED Platinum building, I probably can't do as much for you, but 10 to 30% is what we achieve at the meter. That translates into much larger numbers at the source. We found out that when we optimized a building just around hourly energy prices, as a byproduct, we got a 30% peak demand reduction. Now, it should make some sense to you if you're optimizing around prices. They're highest on the hottest days, middle of the afternoon on the hottest days. Carbon and energy, we found out that there's lots of ways you can operate a building every day. So we now have a multi-objective optimization algorithm employed. We can get the peak demand reduction, we can get the expense reduction, and we have a whole lot of choices as to how much energy we use to get those reductions. A more recent discovery in the last couple of years, and this explains how we're going to go to market. If you bundle storage with just about any other energy efficiency technology in a building, we'll double the payback. You put a new chiller in, I'm going to use that chiller to charge the building at night. So I'm going to take much greater advantage of that new piece of equipment. You put a variable speed drive on a fan or a pump, my storage will figure out a way to take a greater advantage of that new piece of equipment. So we've run the numbers with a number of technologies, a number of companies. Daikin is probably the company we've worked with the most on their mag bearing chillers. So that leads to how we go to market. We're not going to become a big Johnson Controls or Siemens. There's a lot of folks have figured out that they can make a lot of money by bundling our storage with products and services that they already sell. And if we can double the payback on those products and services, they're going to sell a lot more. They like the idea that this will give them a service relationship with these customers, give them more opportunity to sell, to see things. The models that we create in doing all of this provide these channel partners and building operators with insights that just weren't possible before. These are really high fidelity models we build, hourly accuracy, they have to be. Large cities, New York, Baltimore, Washington, Atlanta, all of Texas, because of wind, they have really high prices every afternoon in the summer. Los Angeles is known for its grid congestion. So big cities is our target. I should tell you, though, that the science that we're employing of thermal mass control is applicable down to a residential home. One of our PhD students at University of Colorado Boulder defended his dissertation a year ago. He took 100,000 homes with air conditioners, and he showed how he could take 20 to 30% of the cost off of the operation of the grid in a very large market, just working with the grid operators with residential air conditioning. It's amazing what you can do to thermal load even in homes. Multidisciplinary. So over on the right is the engineering team. Dr. Henza, second from the right, is a professor at the University of Colorado Boulder. We have a long-term R&D and licensing agreement with the University of Colorado Boulder. He insists on mentoring graduate students. The two gentlemen on the bottom are his graduate students. There's 3 or 4 others that have been engaged in our program. Any one of his students could take you on a discussion of grid markets and operations. They're in the architectural civil engineering program. The one on the lower right, Dr. Pavlak, this is his dissertation. The dissertation subject is optimizing a portfolio of large commercial buildings against multiple grid markets. In this case, he did it against the energy market, the capacity market, and the frequency regulation market. And we're talking about optimizing these portfolios every day against grid markets. The two gentlemen on the left, we just added a president and a chief operating officer in July. We've gone now from being a bootstrap company, an engineering company, to a real company that can market and sell. The gentleman on the far left is a long-standing executive in the HVAC industry. The other gentleman has been working in the defense industries, U.S. government, so when it comes to security, delivery of product, we got the start of a team. I should tell you that Dr. Pavlak, what he's going to do first with this, we've been broaching the subject with a number of universities. In fact, that's what we would use the Ocean Exchange dollars for. Notre Dame's probably at the top of the list, but we've broached the subject with Princeton, NYU, University of Colorado Boulder, and somebody approached me from Rutgers yesterday. Maybe we'll talk to them. We've deployed in these buildings, Willis Tower on the far left. On the bottom, United Airlines building, a LEED Gold building, about to become LEED Platinum. Upper right of FAA Headquarters in Washington, D.C., we just deployed in August. We're going to continue that for another year. That comes to us through the Green Proving Ground program. Just this core business, we aim to get to a nice business in 5 years with that team. But this is what gets most of our investors excited, and this is what gets us excited. We want to get to that scale where we become valuable in a big city. We know the international market is 2 to 3 times the size with 2 to 3 times the energy prices. Carbon now we can talk about. That may be the biggest market of all. And with that, Brad?
So buildings have been thermal flywheels forever, and what you've done is you've added a control system to that to optimize into arbitrage, and I applaud you for that. Are you changing the temperature delta that the customer experiences, and if so, how much? And if not, how much does adding delta gain the system in terms of added efficiency?
Changing the delta, we have a lot of temperature flexibility at night when people aren't in the building, and that's important to us. During the day, we'd like a little bit of temperature flexibility. Typically, the buildings say 72 to 75 is the range they allow us to operate in. So if I want to save all that stored energy till late in the afternoon when prices are really high, I might maintain 72 degrees all the way through the morning and start to ramp the temperature up to 75. But by terms of their agreements with their tenants, they're constrained to 71 to 75. 71 degrees in the summer, women wearing summer dresses, it's a little cold.
Okay. And I'm drawing a blank. I have another question lined up for you that I'll come back to.
You can always come back. Over here on the left.
Thank you, great presentation. I know you mentioned that you didn't really want to change the infrastructure of the building, didn't just use the concrete and drywall. But is there a better material? Like, so for future lean plasma or platinum buildings, could you incorporate something into the concrete to make it a better heat exchanger?
My professor is German. One of my director of engineering is German. They remind me every week about how in Europe they build much better buildings for this purpose, thermally massive buildings. Probably the other idea I hear from them often, they think rugs are a really stupid idea. They would like more direct coupling from the air to the concrete surface. So they would prefer buildings, and they say this is more than what you see in Europe. The rug gets in the way of thermal transfer. But
so you didn't think about this into the design of the building?
You could do that, but otherwise, no. We like exposed concrete. My professor's favorite building, we were invited into the Museum of Science and Industry. I turned it down. I decided if we succeeded there, there's probably 3 other buildings in the world that we could apply that to. But think of all the exposed concrete, marble, stone, 20-foot thick walls holding back Lake Michigan, little porthole windows. So everything you put in the building stays in the building and gets absorbed by all the... They were going to do an exhibit for us.
Oh, really?
But instead, we went into the United Airlines building, Willis Tower. That's where our market is.
Makes sense. Thank you.
Okay. Here on the right, Vince.
Interesting presentation, thank you. You had listed on one of your graphs emergent megacities. Last I checked, there are about 35 megacities around the world, the vast majority of which are in the coastal zone. Have you given much thought in your business modeling about how you might approach and communicate this concept, even if it's just standards that might be developed for these other cities, international cities, because this could be a significant energy savings and therefore a reduction in concomitant impacts?
We don't have the bandwidth for too much discussion. I can tell you after the nukes went down in Japan, they invited us over to Tokyo to talk. Tokyo Electric, MIDI, the Building Owners and Managers Association in Japan. Here they were faced, absent nukes, they had to set the temperature set points in their buildings at 87, 88 degrees by law. With our technology, they figured they could get it down to 79 because they cool a lot at night. It didn't happen. Abu Dhabi, they said, we have enough money, but we're building, the buildings are going up faster than we can build the electric system infrastructure to support. They wanted to make it code so they could fit more buildings on less infrastructure. I think that's going to be the big dollar item for your emerging megacities. I mean, everybody's moving into cities. New York used to be the biggest city, and then Mexico overtook it, and now I think there's 10 cities larger than New York City. So a big effect on the billions of dollars of infrastructure.
Right. Here in the center.
I can see why you like the LEED buildings and newer buildings, but what would it take to implement this, both in terms of cost and degree of difficulty for older buildings that don't have as much documentation and arguably need this technology more?
So we should talk about FAA Headquarters. We work in old buildings, new buildings. It really doesn't matter much to us. It's plug and play if it's a newer building. We like really nice building envelopes, so that can be a modern glass building, or it can be one of those old buildings with 10-foot thick limestone walls and little windows. Most of the control systems you have a 15-year life, so even an old building probably has the controls. Right now we stay away from buildings that are under a couple 100,000 square feet. Typically they don't have control systems we can communicate with, and they probably don't have a building engineer. But the old buildings and new buildings really doesn't make any difference to us.
Over here on the left.
May have answered part of my question. I see that your business model that you basically target, multi-floor buildings. Have you guys looked at maybe large national retail stores? Is it applicable to that? They're usually, if you take a Walmart or a Target, single floor buildings.
We have, there's so much opportunity in big grid congested cities, and that's where most of my expertise lies. So we looked around inside big cities and we saw tall buildings. We saw 15 markets, all those buildings concentrated in 15 markets in the US. It's a much easier way to start. There are many other people that have been researching thermal mass control going back into the 90s. The focus has been big box retail. It's a much simpler application.
I see.
On the other hand, when we talk to Kohl's, at their central headquarters in Milwaukee, they have this kind of control over the temperature inside their building. It makes that big a difference to whether people come to their buildings and buy.
Right.
So we would probably have a lot less temperature.
Understood. Thank you.
Temperature flexibility.
Well, I just have a quick question about your revenue model. Am I to understand that this is a subscription-based, where the client or the occupant is paying a certain amount? And if so, how is that amount calculated? Is that by square footage or on their savings? Or are you just capturing the revenue for your company based on the savings that the client is maintaining through their energy costs?
So the first answer will be, remember, we're going to market through other people. And they have their own business models, their own way of doing business with customers. Having said that, the approach that most of the buildings we've talked to like, we know how much money we're going to save them, and we know it pretty accurately. We'd like to capture an annual fee that's 15 to 20% of that total. A fixed price per square foot. They would much rather have a fixed price. And it's a really hot summer with high prices. They would rather capture all that extra revenue, extra savings to offset their underlying exposure to electric prices. So fixed price, annual fee, monthly fee, we're indifferent. And that's mostly what we're talking to channel partners about, and that's what they would rather have also.
Great, thank you.
Brad, for a follow-up.
So the one I forgot before, what does it cost to bring a large building online if you don't get your hands on the architect's construction details? And then the other part of this is the group that has the largest incentive to see you succeed are the power generating companies who would no longer need to build additional peak capacity. Have you had any conversations with getting them to fund this to get their costs down?
First, yes.
Use the mic here.
Yes, first question, the cost to deploy. $25,000 in a 1 million square foot building, $25,000 in a 500,000 square foot building. The cost to deploy is pretty much the same. Willis Tower was an exception. You talk about an extraordinarily complicated and old building, $50,000. In New York City, the payback on $25,000 is about 2 weeks. In Chicago, it's a whole month. This is inexpensive. If they don't have any drawings at all, we can send one of our engineers into their building, spend half a day to a day, and get it all down. Generators. This whole concept was born while I was doing NOx control strategy for First Energy in Akron, Ohio, the largest coal fleet in the country at the time. They're the ones that introduced us to buildings. They tried to pull this off in their company and decided that utilities have their stripes, and as badly as the executives wanted to pull something like this off, they said, we just don't have the people that would know how to do this. The most interest we get, it's not the peaking. Peaking is a small carbon issue, it's a small cost issue. The coal-fired guys, the nuke guys, especially with the onset of wind at night, there's too much energy on the grid at night. In the Midwest, prices go negative. We're overbuilt on nuke and coal plants. This has been a problem we've had in the Midwest since the oil embargo days. We built all these nuke and coal plants, and then the industry fell off a cliff and never developed. Think negative prices at night. So if you're a nuke plant owner, you lose money at night, and you have to make enough money during the day to offset that loss. Now, daytime prices are depressed because gas prices have gone down, and that dictates electric prices at the margin during the day. Nighttime prices, they're losing more money because we have more wind on the grid at night when we don't need energy on the grid at night. So it's a tough place for the coal and nuke guys. They would love storage, somebody that absorbs energy at night, boosts the prices a little bit at night. And if the effect of that is that peaker plants never have to turn on, they don't really care. They would retire their marginal coal plants, the lousy ones. They would much rather have this kind of a profile. So the big money is the nuke and coal guys.
And one last question here in the center.
Thank you for your presentation. As a consultant, if I'm trying to convince my client to use your services, and you're telling them that they have to pull up all the carpet, what kind of efficiency improvement are they going to get if I successfully talk them into doing that and implementing your strategies?
Think Willis Tower, the graph that I showed. Mm-hmm. It's a pre-oil embargo building, so one of the worst designed buildings that you'll ever set foot in. Mm-hmm. Single pane windows, air leaks, rugs everywhere. And we got that kind of performance. If my German partner just tells me, look, if you really want to do it, you want to go over the top, there's a lot of things we could do better. But we take crummy buildings, we take good buildings. I like a really good building envelope. Willis Tower is the worst building envelope in all of Chicago, and we still did that. So rugs, no, you don't have to tear up rugs. You don't have to change anything at all. 2 to 4 weeks to deploy, you get to try us out, and if we don't perform in a month's time, you can tell us to go away and we'll go spend our time in some other building.
Thank you very much.
All right. Vince Cushing, QCoefficient. Thank you, Vince. Great job.